Recently, I joined Huawei Technologies, which is one of the major IT companies in China. Huawei has created a new research lab in Hong Kong. So now I'm working in the lab in Hong Kong. Okay, so let's start the talk. So first, I will explain the motivation of the work, and then I will explain three methods for web search, namely regularized latent semantic indexing, group matrix factorization, and matching in latent space. Okay, so these are the queries manually collected from the search log of Bing. So if you see them, then you can see that they represent the same search need, the same search intent, distance between Sun and Earth, like how far Earth Sun, distance from Sun to Earth, etc. So there are many different variants to represent the same search intent. So due to the flexibility of language, a search intent, a search need, can usually be represented by many different forms. In other words, different queries can represent the same search need, right? And so far, search is still mainly based on term-level matching. That is, if the query terms occur many times in the document, then the document may be viewed relevant. Okay, so that means if the searcher does not formulate the query very well, then it's likely that she may not find the document she is looking for, right? So this actually poses a great challenge to search. If you look at all the hard cases in web search, you may see that most of them are due to mismatch between the query and the document. Let me show you another example. So this is for query YouTube, right? You have many different variants, like YouTube, and even people type my tube, our tube. Okay, so if you type this at Google Bing, you can still find YouTube. Okay, so in this project, which we call semantic matching, so we try to develop advanced machine learning techniques to solve the mismatch problem. Okay. So this is how we view this problem. So traditionally, search is based on term-level matching. So term-level matching. So if the query terms occur many times in the document, then the document is viewed relevant. So we want to expand this. Not only conduct query document matching at term level, we also want to conduct matching at several different levels, representing different semantics. So at phrase, word sense, topic, and structure levels. Okay, for example, at phrase level, we want to match hot dog. Actually, exactly means hot dog, not hot and dog. And at the word sense level, we try to match NY to New York, for example. And at the topic level, we try to match Microsoft Office with Microsoft PowerPoint, Word, Excel. Right? And at the structure level, we really want to match how far is Sun from Earth with distance between Sun and Earth. So we try to develop different techniques to enhance search relevance. So this is what we try to do in this project. So let me give this from another viewpoint, from the system viewpoint. So we want to actually conduct better query and document understanding and conduct matching between the query and document with richer query and document representations. So this is at the query side. Suppose we have a very rich query understanding. Suppose the query is Michael Jordan Berkeley, and there is a typo. So first, we want to correct the typo. And then we want to identify the phrase within the query. So Michael Jordan is a noun phrase. And we try to find similar queries, like Michael I. Jordan, etc., which would be similar to the input query, and identify the topics of the query. Maybe it's related to machine learning, etc., and identify the structure of the query. So Michael Jordan is the main phrase, etc. So we want to do better query understanding. And at the document side, we also try to do better document understanding. Similarly, we want to do phrase identification, key phrase identification, topic identification, and title structure identification, etc., to have a better understanding on the document. And after that, with richer query and document representations, we can conduct matching between the query and document, and to really help the user find the information to enhance search relevance. So this is the basic idea in the project. So actually, this problem is not new. In the long history of IR, people try to develop different techniques to solve the problem, like query expansion, pseudo-relevance feedback, etc. But in web search, things have changed somewhat. At least there are two things which are new. One is that there is a huge amount of data available, particularly log data available. Another thing is that new advanced machine techniques have been developed recently. So this is exactly the motivation within our project. We try to leverage advanced machine learning techniques and a huge amount of data to try to solve the mismatch problem. So in order to do a better job than traditional methods. So you may ask a question, what's the relation between matching and ranking? Right? People also talk about relevance ranking, etc. in search. So in one word, so this is the relation between matching and ranking. So in search, we first conduct matching and then ranking. Given a query and document, you first decide whether they can match very well or not. And then if you have a number of documents, you calculate the matching scores among the documents, and then you do ranking. So from the viewpoint of machine learning, there are actually two different tasks. So in matching, the prediction is about matching degree between the query and document. You want to really identify whether the query and the document can match with each other very well. And in ranking, actually, the goal is to create a ranking list of documents. So the models are also different. In matching, the model is defined over a single query and a single document. But in ranking, the model is defined over one query and a number of documents. And the challenges are also different. In matching, so the mismatch is a major challenge, as I have explained. But in ranking, the major challenge is how to do a very good job on the top of the ranking list. Because usually, in web search, you really want to have the most relevant documents ranked at the top. Okay, so the query document matching problem is not only limited to search. You can see many similar problems in different applications, like collaborative filtering, image annotation, dating, machine translation, and drug design. And in all these applications, actually, you need to solve a problem of matching between heterogeneous data from two different species. So Professor Ghosh talked about collaborative filtering on the first day about collaborative filtering. And actually, it's a very similar problem as query document matching we are considering here in search. Okay, so let's move to the first method we have developed. So here, we try to use machine learning techniques to help conduct query document matching at the topic level. So, so there are many methods proposed in the literature, like LSI, PRSI, and LDA, which are topical models and which can help, in principle, query document matching at the topic level. But the challenges for them is that they cannot scale up well. So here we try to solve the scalability issue. So we consider the approach of metric factorization with regularizations on the topics and documents. So, so in this way, we can decompose the learning problem and make the learning algorithm parallel. Professor Park introduced non-negative metric factorization the day before yesterday, and so I don't want to go to the details. So here, again, we try to solve the matrix factorization problem. So we are given a document and a term matrix. The matrix is very sparse. Okay, so we want to factorize the matrix into two matrices, U and V. So U represents topics, and V represents document representations in the topic space. So we can formalize the problem in this way. We have a Frobenius norm-based loss function, and we impose regularizations on the U matrix and V matrix, so on the topics and the documents. So here we consider L1 regularization on the topics and L2 regularization on the documents. So in principle, we can consider 4 combinations. So L2, L1 on the topics and documents. And it turns out, based on our experiments, the L1 on topics and L2 on the documents is the best choice, because this will give us sparse topics, which will help us to easily understand the content of the topics. In the meantime, help us to improve matching between query and document in search. So L1 on topics, L2 on documents turns out to be the best choice for us. And we found that, so when compared with existing methods like LSI, PRSI, and LDA, our new method called regularized latent semantic indexing works equally well in topic discovery and web search. But our algorithm can have a scale much better than existing algorithms. So let me explain how we use the topic model in query document matching. So given a huge document collection, we actually conduct regularized latent semantic indexing. That means we factorize the input document term matrix. And then we can project the documents into the topic space to represent the documents in the topic space. And given a new query, we view this new query as a pseudo document. And we use the projection and also project the query into the document in the topic space. And then we calculate the similarity between the query and all the other documents to really find similar documents in terms of topic similarity. Okay, so this is how we use the topic model. And so to learn the topic model, RSI, we just adopt the conventional approach. Because this is not a convex optimization problem, so we actually take a greedy approach. So to iteratively update the 2 matrices, U and V, the topic matrix and the document matrix. So fix one and update the other one and iterate this process. So when updating the matrix U, we use coordinate descent method. When updating the matrix V, we just solve the analytic solution. So this is the pseudocode of the algorithm. So we have implemented the algorithm on a single machine and also on multiple machines based on either MapReduce or MPI. So the algorithm is very simple, as you can see. So this slide shows a scalability comparison between our method, RSI, and other existing methods on topic modeling. So RSI can handle, for example, 2 million documents and 2 million terms on a single machine with 24 cores. So in contrast, for example, other methods like PLDA or PLDA Plus needs to use 2,000 processors to handle 2 million documents and 200,000 terms. They have to drop a lot of terms in order to handle so large data set. So that means RSI has a much better scalability than many existing algorithms. Perhaps it is one of the best algorithms in terms of scalability in topic modeling. So this slide shows topics discovered by RSI and other methods, LDA, PRSI, LSI, etc. I don't know whether you can see clearly. And so the topics discovered by RSI are comparable with those discovered by existing methods. And so almost all the topics discovered make sense to humans. And so this graph shows accuracy in search relevance. So lambda rank is a state-of-the-art of learning algorithm for ranking in web search. So when you incorporate RSI as a feature of lambda rank, you can significantly improve the search relevance. And that means RSI can really help to do a better query document matching and improve the overall ranking performance. And so if you drop some terms, so sometimes people have to drop terms in traditional topic modeling methods. If you drop some terms, then we observe that the accuracy will drop quite significantly. That means it's better to keep all the terms as input in a topic modeling method. So this is the first work. So with RSI, we can easily handle millions of documents, either on a single machine or on multiple machines. But the number of topics we can handle is still limited. It's something like 1,000, 2,000. So we wanted to further enhance the scalability of the method. So we have developed another method called group matrix factorization. So the motivation is to further enhance the scalability, particularly the size of topics. And again, we take the matrix factorization approach, and we consider RSI and NMF as a basis of the approach. So here we assume that there are some semantic classes available. So the documents have already been classified into the semantic classes. So there are many taxonomy available, like ODP or Wikipedia, etc. So given a set of documents, it's very easy to use a supervised method to classify the documents into the classes. So the classes usually represent general topics, right? So it's easy to use a supervised learning method to assign a class label to each of the documents in the document collection. And then we assume that there are some topics shared by all the classes. And there are also topics specific to each of the classes. So in this way, we can further divide and conquer, take a divide and conquer approach to partition the problem and to further enhance the scalability. So this is the idea. So suppose, again, we are given a document term matrix. And so we can partition the matrix based on the classes of the documents, right? So each part corresponds to one semantic class, right? So suppose each document must belong to one of the semantic classes. And so, for example, D1 corresponds to the documents belonging to the first semantic class, first category. D2 corresponds to the second category, etc. Right? So then we can, when we do factorization, we can really conduct factorization separately based on classes. So for example, for D1, we really only need to think about factorizes into two matrices, U0, U1, and V1. So U0 means the topics shared by all the semantic classes. It makes sense, right? So there should be some common topics shared by many different classes. But there are also some specific topics only belonging to the first class. So here we just try to factorize D1 into U0, U1, and V1. Okay, so then we do this for each class. So this is a formal formulation. So we have a loss function. So you can come up with different loss function. And you can also impose a regularization on the shared topics, as well as the class-specific topics, and also on the document representations. And more specifically, when you adopt IRSI as a basis mechanism, then you have the formulation like this. So this slide shows the algorithm. So it's just a very simple extension of IRSI if you use IRSI. So we repeatedly update U and V. But here we have multiple U's. So we first update the shared U. And then for each class, we update its corresponding U and V. And then we repeat this process. So this slide shows the performance of group-based IRSI and IRSI, group-based NMF and MF. So the x-axis represents number of topics. So the two graphs on the left shows result on one data set. So you can see that when the number of topics increases, so the performance of group-based IRSI here, actually for the group-based IRSI, the execution time does not change so much. But for conventional IRSI, but for the IRSI, so the computation time increases drastically. So that means when we have partition the data into different classes, semantic classes, then we can really improve the scalability and efficiency. And so this is the result for MMF. So again, group-based MMF performs much better than the original MMF. Okay, so these are the result. The graphs on the right are the result on the other data set. So for this data set, the original RSI and MF can even not finish the result when the number of topics increases. So again, you can see that the group-based versions have much better scalability. So this slide shows the result obtained by group-based MMF or RSI. And the results are quite comparable with the original algorithms. That means even with the partition, with the group-based versions, we can still keep the accuracy, but improve the efficiency and scalability significantly. So these are the results for search relevance. You can see that group-based version can perform equally well as the original versions. Okay. So next, I will explain another method for query document matching. So here we conduct query and document matching in a latent space. So you can also view it as a kind of topic model, but a different approach. So suppose we have queries in the query space and documents in the document space. And there are similarities between queries in the query space and the similarities between documents in the document space. And there is also click-through data available. That means queries and documents are associated. So by click-through here, I mean when users submit queries, they must click some documents. So that means the queries and documents are linked during the search processes. So we can collect the data and then take the data, the click-through data, as training data for our purposes. So the idea here is, so given queries and documents and links between queries and documents, we try to project the queries and documents into a new latent space, and with two linear mapping functions. And the hope is that in the latent space, we can really make similar queries and similar documents get together. So because we have similarities in the query and document space, so we try to keep the original query document similarities in the latent space. And in the meantime, we also know the associations between queries and documents. We also want to leverage that information, or also want to reflect that information in a new space. And the hope is that in the new space, we can really represent query and document similarities. So actually, this is not limited to query document matching. We can view this problem as any matching problem between heterogeneous data, right? So this is some example. We obtained from some toy data set, a real data set, but toy data set. So there are two spaces. One is image data. The other is keywords. So some keywords are associated with some images. So certainly in the image space, there are similarities. In the keyword space, there are also similarities, right? And with our method, with two projecting functions, we can actually project keywords and images into a new space. You can see that in this new space, similar images and keywords are really grouped together. So the similarities in the new space can really represent the similarities between heterogeneous data. Okay, so let's look at the formulation. So this problem is not new in some sense, because in statistics, there is a very famous method, traditional method called the partial least square, PLS. Actually, PLS can be employed exactly in this problem, although the original PLS was proposed based on different motivation. So here, we are thinking about supervised learning method. So we have two spaces, X and Y. So in our case, query and document spaces. So as training data, we have X, Y, R triples. So X is a feature vector belonging to the first space. Y is a feature vector belonging to the second space. So R is the response. So for simplicity, let's assume that R is either 1, +1, or -1, right? Similar or not similar. Okay, so you can easily extend this to real valued cases. Okay, so we have training data like this. So we are thinking about two different mapping functions, try to map the feature vectors in the two spaces and to respect the response, to make sure that similar X and Y should get closer and the dissimilar X and Y should be far apart in a new space. Okay, so we can easily come up with the objective function like this with dot product as a similarity function in the new space. Okay, so in PRS, we actually assume that the two projections are also normal. Okay, and so we know that so this formulation actually has a optimal global solution, and with SVD we can solve this problem. But again, we have a scalability challenge here, because in order to solve this problem, we need to solve SVD. It's hard to make SVD scalable. So here, again, we try to use a regularization approach. Instead of assuming that the two projections are also normal, we assume that they are sparse or are smooth. And we impose L1 and L2 regularizations on the two mapping functions. So we need to actually impose both L1 and L2 regularizations on the projections. Otherwise, we'll have some trivial solutions. So then this is the formulation. And in this way, we can easily partition the problem and do the optimization in parallel. Okay, so we can keep Lx, one of the mapping functions, fixed, and updating the other mapping function, Ly, and iterate this process. So here are some conclusions from our result. So to compare with conventional PRS, our newly proposed method, RMLS, has much better scalability. So the efficiency can also be significantly improved. So the compromise is that we don't have a guarantee that we can find global optimal. Okay, so these are some experimental results based on PRS and RMLS we have proposed. We can see that NPRS can really enhance the accuracy ranking in relevance ranking. And RMLS, the new method we have proposed, can really improve the scalability and efficiency of PRS. So in this talk, I have introduced three methods for query document matching in web search. So the main motivation for us is to make the algorithm scalable. So we try to use regularization techniques and to formalize the problems and to make them scalable and parallelized and then scalable. So we observe that all the methods perform equally well as the existing methods, but they have much better scalability and efficiency. So these are the publications in the project. We have developed a group of techniques for enhancing query document matching. So when combine all of them together as features of ranking model, and we can really improve relevance. Thank you. Okay, so the question is, in the RMLS work, currently we use +1, -1 derived from click data. Is it okay to use click number as response? Is that true? Yeah, the answer is yes. You can easily extend it. And so you can think about using different response variables.
Will that affect the accuracy of?
Actually, here we use +1, -1 binary values for ease of explanation. In our experiment, we use the number of clicks, and you can also take logs sometimes. They work equally well.